I've decided to record a video of me talking through the atomic theory notes since I will most likely not be in class tomorrow, and I would like to actually go through these notes so you have a better understanding of what is going on. So you have two things you need to do. Pay attention to this video as I talk through the notes, and then cross-reference what I have in these notes with the atomic theory notes that you created as a class and make any changes to your atomic theory notes on that Google Slides file that I posted for your class. So we'll go right from the beginning. As you can see, the first thing you were required to do in these filled-in notes was to draw an atom. And the atom could have looked like anything. It could have looked like any model that has been around. So this model right here, or this drawing of the atom, was one that I found online. But basically, this is more of a later model, but not the latest. So let's start at the beginning. So there was a time back in 400 BC that there was this guy, this Greek philosopher, sitting around thinking, and his name was Democritus, and this was a long time ago, 400 BC. BC is before Christ, so we're thinking like, 2,400 years ago. Well, he thought that matter was made up of atoms, and they were these indivisible, pieces of matter. And so what he thought was this indivisible piece of matter was just some sort of sphere, and that's all he knew. And which is actually pretty impressive that he actually thought that all the stuff was made of these little things. Well, a little while later, another philosopher, Aristotle, I'm sure you've heard of him, possibly, he disagreed with Democritus, and he thought that everything was made up of four elements. One is earth, the other is air, the other is fire, and the other is water. So those are the four elements of matter. And like I said, this was 100 years after, so it was 300 BC. So pretty close in time, relatively speaking. Now, the one thing that Democritus and Aristotle were the same of were that they were both philosophers and not scientists. So I know they disagreed, but they were only philosophers. And the reason they were only philosophers because the only way you can become a scientist is if you actually have experimental evidence to support your ideas. So a lot of time passes by, and not until about the 1800s, there was this guy from England named John Dalton, and he decided to start talking about atoms again. And he also figured that an atom was some sort of just indivisible, indestructible solid sphere. So here is his model. Doesn't look much different than, say, the Democritus atom model up there. Now, here's how his was different. I know it doesn't look different, but his was different because he actually gathered experimental evidence to support his model of the atom. And what he did is he actually made measurements of masses of elements that combine to form compounds. Now, compounds are molecules that form more than one atom. And what he found was that no matter how large or how small the sample of his substance was, the ratios of the element in the compound was always the same. The mass ratio, in fact, was always the same. And so he was able to come up with an atomic theory, and this was really the first theory. And it was good to go for the purposes of what he was doing. Most of it is still right. However, there is a thing or two that has now been determined to be different. But that's okay. So here's what he said. He said all elements are made up of atoms. That agrees with Democritus. What he also said is atoms cannot be divided. That also agrees with Democritus. However, that's not the case anymore. We now know that atoms can be divided. So he also said that atoms of the same element have the same mass. So if he was to find an element of carbon, he would find that all atoms of carbon have a mass of 12. Oxygen has a mass of 16. Nitrogen has a mass of 14. We'll learn more about that later. He also said that atoms of different elements have different masses, and we will also find out later that every single element has a specific mass that's different than everybody else's. He also found that atoms combine to form compounds, and the compounds have a fixed composition. That means that the ratio of the masses of all of the elements is always the same. So for instance, looking at these atoms here, oxygen, hydrogen, nitrogen, carbon, they all make up compounds in various ways. Here's one compound of nitrogen oxide. It's one nitrogen and one oxygen. And what you'll find is if you gather any amount of nitrogen oxide, what you'll find is there will be a mass ratio of 14 for nitrogen to 16 for oxygen. You'll find that every time. Water is made up of 2 hydrogens and 1 oxygen. And so you will find that because hydrogen has a mass of 1, so 2 of them together was a mass of 2, and oxygen having a mass of 16, water will always have a 16 oxygen mass ratio with a 2 hydrogen mass. And so the nitrogen can hook up with 2 oxygens, like so, and the mass ratio is the same no matter how much of the substance you gather, and then carbon dioxide as well. So there you go. We'll learn more about compounds and why they're named the way they are and how those numbers and letters come together. So, after Dalton was done with his work, there was a time later that the atomic theory developed more with more experimental evidence. And there's this experiment that J.J. Thomson did with the cathode ray tube. And I actually have 2 ways to show you this. One is I can actually show that there can be a light beam that goes through this cathode ray tube that can be bent. What you can also do is see somebody else do it and explain it on this video link, which I will post on Google Classroom. So basically what happened is, in the cathode ray tube, there is a stream of light that goes across, and actually what the light is, it's excited negative particles from the metal that's inside the cathode ray tube being shot across. And because those negative particles are being shot across, and that whole glow is negative, you can put a magnet up to it, and because a magnet has charged ends, negative and positive charged ends, you can actually bend the light beam either towards the magnet or away from the magnet. So if you have the negative end of the magnet and you go up to the negative charged light beam, the light beam will actually repel and move away from the magnet because like charges or like poles repel. And then when you flip the magnet to the other side, you will see that with that positively charged end of the magnet, when it gets put up to the light beam, it would actually make the light beam bend towards it because the opposite charges attract each other. And so the guy that did this was J.J. Thomson. And so what he ended up saying was atoms actually aren't just these indivisible structures. There's actually something else going on in there. There's some charged particles in there. And he actually called the particles electrons. And the electrons have a negative charge, and the mass is really small. The mass is 1/2000th the mass of a hydrogen atom. So you take the whole hydrogen atom, and just 1/2000th of that is the electron. So here's what Thomson's model looked like. He said, you know what? We have this sphere that the atom is, but within that sphere, you have these negative particles swimming around. And because an atom is neutral, he thought that these negative particles were swimming around in like a positive soup or a positive pudding. And he was English, and the English really liked to eat plum pudding, So what he called this was the plum pudding model. You could also say it looks like a chocolate chip cookie model. All right, so after Thomson, there were other particles that were discovered. The proton was discovered, and that has a positive charge. So there's actually particles in the atom that have a positive charge. Neutrons are also in the atom. These were discovered in 1932 by James Chadwick. Those were found to be a neutral charge, so neither positive nor negative, but neutral, so no charge at all. So here's a table of what's going on with the subatomic particles. Subatomic meaning below the atom level, smaller than the atom level. So here we go, proton, neutron, electron. If you were to do a symbol, P plus, because P is for proton, plus for the plus charge. Electron has an E minus, E for electron, minus for negative, and then neutron is just N, no charge. And so when you have a proton, the proton has a 1 plus charge. So if you have 10 protons, you have a 10 plus charge. And chemistry shows it as the number and then the plus after it, not a +1 charge. Neutron, 0 charge, and then each electron has a 1 minus charge. So if you had 10 electrons, you'd have a 10 minus charge. So here are the masses. Like I said, electrons was about 1/2000th the mass of hydrogen. Well, if you're comparing that mass to the mass of a proton, if it has a mass of 1, then a neutron also has a mass of 1, which means those two have the same mass, essentially. An electron is just a much smaller mass than those two. So all of the mass of an atom really are associated with the protons and neutrons. We'll learn more about that later. All right, so let's talk more about the proton specifically. So the atomic theory, which we have the atomic theory, it's a good explanation, but it can change as more evidence comes to light. So there was this experiment called the gold foil experiment that Ernest Rutherford did. And here's the link to the video, which I will put on Google Classroom so you can link it and watch it. But basically what happens is there are these positive particles that get shot through basically a thin piece of gold foil. And these positive particles are called alpha particles. They were expected, based off of what J.J. Thomson said, they were expected to just go right through the gold foil because the positive and negative charges were just kind of just swimming around and it would just go right through it. However, what he found was those particles, a lot of them would go through, but there were a few that would get deflected either straight back or to the side or just deflected in a pretty substantial way. And so what he thought was, okay, if most of them go through, then the gold must be made up of atoms that have a lot of empty space. But then, because some of them didn't go through and hit very specific spots and bounced off, there's got to be these spots in the atom where the spot or the center of the atom has to have some sort of positive charge to deflect the positively charged alpha particles being shot at it. So basically this paragraph explains it. So Ernest Rutherford in 1909 said that it was empty space, but he also said there was a nucleus of an atom that was very small and very dense and concentrated right in the middle of the atom. And so his model was actually like a stadium. So why do I say it's like a stadium? Because think of yourself throwing a penny and having the penny land in the middle of the stadium. And then think of how small that penny is in the middle of the stadium. And then think of how big the stadium is with all of, the fans around it and all of the seats and just how massive that is. That penny would be the same proportion of size to the nucleus as the stadium is to the whole atom. So this is ultimately a picture of Rutherford's model. He basically said there's this center positive core, this nucleus, and these electrons are going around the atom in some way. He didn't know in what way, but he just knew that it was happening. All right, so we're getting more modern here, and we're getting close to the end, but the next guy that came about was Niels Bohr, and it was 1913. So you notice we're not spending a lot of time here. We went from Dalton in the 1800s to now 1913, whereas before Dalton, we were going all the way to 400 BC with Democritus and 300 BC with Aristotle. So Niels Bohr said he thought the electrons were found in energy levels, because what happened is when he charged gases, he saw these bright lights shoot out, and he saw them in the spectrum, and he assumed that because those charged electrons in the gas were showing light, that the only way they could show light, because it took energy, was for the electrons to move to a different energy level. And so that light was just a representation of electrons moving to different energy levels, which means that the electrons would have to originally be in a specific energy level. And so what he came up with was a model of a solar system. And so think of our solar system, the sun in the middle. In this case, the sun is the nucleus, the positive charged nucleus. But what he thought was there was a pathway close that had 2 electrons. And then he said there was another pathway further out that had 6 electrons. And then he said there's a pathway even further out where there were even more electrons, and in fact there would be 10 electrons on that outer shell. And so he was seeing the gases being charged and those lights emitting, because electrons, when they emitted the light, they would actually be moving from level to level. Okay, so we're almost to the end here, but there's one more guy that came about, and his name was Erwin Schrödinger, and he actually used mathematics to form what is now the newest model, I guess you could say, although I shouldn't say newest because there's always some developments, but he had what was called the electron cloud model. And so what he said is the electrons don't necessarily follow these perfect orbits on these perfect energy levels. They actually move around and aren't necessarily always located in the same space. However, there is more probability that they are located in some space as opposed to other space. And so he just basically said that electrons move around, and if they are in a space more often, he figured there's a higher probability of it being there. And what he showed with his model was that the electrons that were in the part of the space where it was more dense, or where you could find it more probably, was a denser cloud, and then where you'd find the electrons not as frequently was less dense. But you still could find that everywhere in that cloud is just more likely here than out here. So this cloud would be where the electrons that are in the first level would most likely be found. So this is a relatively simple atom, which actually has 2 pluses there. So those are 2 protons, and then those orangish reddish are 2 neutrons. And so that's a relatively small atom with relatively few electrons and few protons. So if there's 2 protons here, that means in this space you will find 2 electrons. And you'll find them more likely here, but you could also find them out there. So these places where these electrons move around and most likely could be found are called orbitals. And so this whole thing is an orbital. This is an entire path the electron could be in. And this is a spherical orbital. There are also other orbitals. So this is what is called the s orbital. There are also p orbitals, and there are also d orbitals, and you could even go further, but we won't. But the p orbitals, which are, the next ones, you would have actually more than just a couple electrons like this. You'd actually have a couple electrons moving around here. You'd have a couple electrons moving around here. You'd have a couple electrons moving around here. And you'd have a couple electrons moving around here. And so that would actually be a total of electrons going around. So anyways, we'll talk about that in just a bit, a little bit more. So here are the scientists that we've really focused on, and these are scientists you'll want in your timeline, which is another assignment you'll be working on in class. But we have John Dalton, going to J.J. Thomson, going to Ernest Rutherford, going to Niels Bohr, going to Erwin Schrödinger, and then you have James Chadwick, who is the neutron guy. So, as I was stating earlier, you can now describe location of electrons as an atom's electron configuration. So, where the orbitals are, those make up the electron configuration. And what that does, the electron configuration does a few things. It talks about energy levels, sublevels, and orbitals that electrons occupy in their lowest energy state or ground state. So Niels Bohr said, hey, when you get the electrons excited, they'll move from one energy level to the next. But when they are in an unexcited energy state, at their lowest state, then that is the energy level they'll be in, or that'll more specifically now be in a specific orbital. And each orbital can contain at most 2 electrons. So here's how it goes, and I've explained this a little bit. So the first energy level only has what is called the s orbital, which is 1 orbital. So if you have only 1 orbital, you have 2 electrons. Now we could really get into orbitals, and it gets pretty deep and pretty heavy, but this is as much as you really need to know. The second energy level, which I talked about and showed, was, well, first, that level has an s, and then also that level has 3 p orbitals. And so you then have 1, 2, 3, 4 orbitals. And because you have 4 orbitals and you can have 2 electrons in each orbital, you have 8 total electrons. And then the third level gets pretty complex, but that level you have an s, that's 1. That level you have p, which is 3 more. And then you also have what are called d orbitals, and that would be 5 orbitals. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Because you have 9 orbitals, you have 18 electrons. So that's not all. Just so you know, the atomic theory is still being developed. And it is being developed to include things called quarks, leptons, charm, up and down, and even more. But we're going to leave it at that because I think you have enough information. So I hope this was helpful, and I hope that you're able to follow along with it. I'm sorry if I stuttered a few times. But use this, pay attention to it, look it over again if you have to, and then compare it to the notes that you have put together in groups, and make sure that all of your answers are right in that, and all your information is completely correct. Thank you.